Welcome back. This is Class 4 on shockwave physics in PM 681. The homework that for next Friday, is by the October 1st class is just problems 2.4 and 2.5 in the book. I found a slight error in 2.5, so I fixed it and reposted the book. So if you have not downloaded the book since August 9th, you need to redo that so that you actually get the problem with the correction in it. So I do that occasionally. As I go through this, I find small errors, but when they're important, I will alert you to the fact that I reposted it and you need to get a new version. So let's go continue. Remember that my contact information is there, and the homework assignments are due to be uploaded on the Blackboard website for the course, and you submit hopefully just one file per assignment. You know, if it's Adobe file, you can put all the pages together easily. So then upload it under the homework assignment file by clicking below on the View Complete Assignment. Allows you to upload your assignment to that link. And so everything is on the web base for the grader to actually look at. Be sure to put your name and the which assignment, and I'm going by just assignment 1 for class 1, assignment 2 for class 2. So a very simple procedure. So be sure to make that your homework is on there. We can look it up, but it does take a lot of extra time for us to do that. And if you don't sign it, then we don't know who submitted it, or at least have your name on it. So please make sure you're doing that. We have a large class, so that'll keep our grader fairly busy. I do the point system on the homework, and as I told you, the grade will be the assessment with the homework and a final exam. And if I believe we need a midterm, I will also do that. But that's after I see how everyone's doing, whether I really feel that you need to have a midterm or not. Okay, the big problem that I've ask you to do is derive the conservation laws for a 2 shockwave problem, and essentially that's a shockwave 2, which is here described in this as this plane. This is very similar to the drawing I did deriving the single shock equation, but notice that instead of the pressure being 0 and the density rho naught, it's the condition behind another shock that is passed in front of it. So the conditions in front of this shock are different than the time before. And it has a particle motion of u1 instead of 0. Because it would be behind a shock front 1. And so that would be the conditions behind a shock if we... I didn't draw it, but you know, essentially there's another shock 1 over here with U1. I didn't think that was necessary, but anyhow. Well, if we, the first 2 are easy. The energy one is a little tricky, and it's basically the mass flowing into the shock here is equal to the density in front times the flow in, which is in the Larian coordinates is U2 minus U1, because this shock wave is going forward, but it's going, so is the U1. The U1 is forward. So you subtract it to give you the Eulerian velocity in this coordinate system. So the area is a cross-sectional area A, so in a small delta time delta t, then this would be the mass that's flowing into the front, or the front is going crossing over, whichever way you want to view it. And the mass going through the back or out the back is then the new density and the shock velocity and layering coordinates and the particle motion, because it's also, this U2 is also to the right. So that's the mass going through the shock jump. Well, mass has to be conserved, so these have to be equal. So you can see it's a little different than the single shock, but it was fairly easy to do. So that balances then and says the mass is rho 1 U2 minus little u equal rho sub 2, the shock velocity capital U sub 2 minus little u2. And remember that rho 1 is equal to 1 minus v over v1 by definition for a continuum mechanics approach. And of course rho 2 is 1 over v2. So that means this is the compression. If you solve this equation for rho 1 over rho 2, you get the v1 over v2 expression from that. That's straightforward, so I'm not showing that. Now each problem here was worth, I think, 10 points, so that was on the homework assignment. Now the momentum equation is, again, there's more than one way to do this problem. I like to use just the Newton's law as the change in momentum. And momentum is mass times velocity, and it's the mass velocity of the material. So the change across the shock front is what we're going to talk about, or another way, better way to say it is that the shock front does work. Remember, work is energy, and it's force times distance is the definition of work. And so the work done by this shock wave is P2 minus P1 times A delta T. And I'm leaving the delta T's out because I took actually the derivative of the mass times the mass velocity. So essentially then, I'm sorry, I got ahead of myself. Let me back up. I'm on the momentum equation. I jumped to the energy equation, which is in my mind because I think that's the little more of a challenge. The force across the shock front is the difference in the force is P2 minus P1 times A, and that's equal to the change in the momentum. That's Newton's law, and that's mass times mass velocity. Well, we know already that the mass is that term, and the change in the mass velocity is just U2 minus U1 across that front. And so that's the change in momentum, and delta T is this mass times this change in velocity. So you can just write down that cross out the common terms, the delta T and the A, and the pressure across that shock front, the difference in pressure from the state ahead of it is P2 minus P1 is equal to rho 1, which is the initial state ahead of it, the density ahead of it, times capital U2 minus little u1 times the delta of the particle velocities, little u sub 2 minus u1. So that's the conservation of momentum, just using Newton's law. You can also do this, like I said, as a flow problem, but it's a little longer, but not too much. But this is straightforward. So that would be the derivation of the momentum or equation, and it gives you the stress or the pressure across that shock front, the change in pressure. Okay, the third problem is the energy or the work done, actually, and the balance of the energy. So this is the jump equation. It gives you the internal energy equation. but you have to balance all the energies that's in this problem. Remember, it's a one-dimensional flow, and if you have in a small area here, delta T, this shock wave does work. And work, let me write it down. If you remember work from your thermodynamics, work is equal to force times distance. And that's an energy. That's the energy that you did to move this material. And of course the shock wave is moving the mass, so that's the energy that it's actually required to do this work, for this to happen. Well, the force, per area is the pressure, so you can write this as P A times the distance in a delta T time, and turns out that ahead of the shock, then the work that's done, behind the shock, I'm getting, again, a little ahead of myself. The difference in the work, the shock 2 does this work, but the flow ahead of it is also moving the materials, so it's the difference in the work that really is the energy involved in the shock wave number 2. So this would be the difference then in the work, and that's an energy. Now that has to equal the kinetic energy plus internal energy in this material, because energy has to be conserved. So the work done by the shock U2 like I said, has to equal the kinetic energy, which is 1/2 mv squared, and the change in internal energy. And we define E as internal energy per gram. And we're actually going to solve for that. So we just put it down in this form. So we have the work is equal to, well, first of all, we got to get the let's see. This is the kinetic energy of the mass behind the shock front 2, or the shock 2, and the material ahead of it is going at u1 squared, or u1 velocity, so that has a kinetic energy. So there's a kinetic energy. There's a kinetic energy in the flow ahead of the shock, and there's a kinetic energy in the flow behind it, and therefore they have to add up. Their energy is not lost or like I said before, is not destroyed or created. It has to equal the energy that's in the system. So here's the kinetic energy difference between head of the front here and crossing the shock into the shock. And then the internal energy is just defined as the energy per mass. And in terms of this equation, then the mass is here. So energy per mass, and the A delta T's cancel out. So it is basically, this term here is the kinetic energy and internal energy. It has to equal the work. So now we just equate those two equations here and do the algebra, which is a little messy, and I substitute just to make the I don't want to write that all the time, so I define that. But if you just look at those equations, that's what we get. And if you do the algebra, and then you'll find that you get E2 minus E1. Let me underline that. That's the change in internal energy, and it comes out to be P2 plus P1 times V1 minus V sub 2 over 2, which is the correct answer. This is a little tricky. If you didn't set it up just this right way, it could be a tremendous amount of algebra. And I didn't want you to spend that time, and I said that in the problem. If you can set it up and see the idea of balancing the kinetic energies plus the internal energy, that has to equal the work done. That's the balance of the energy. And remember, the internal energy is probably mostly thermal, but it can also be creation of defects in the material, such as dislocations and other things. That energy usually, typically, is very small compared to thermal energy in a shock. But you might, for certain circumstances, still have to account for it. So just be aware of that. Okay, so this then derives this very useful equation, which we have used before to tell us what the Rankine-Hugoniot equation is for a shock where the conditions ahead of the shock are not the standard P equals 0, U equals 0, V naught. So if you have a flow, a hydrodynamic flow ahead of it, this is the equations that you actually wind up getting. So I typically like thinking of it in terms of the two shock waves going, because that's what creates the flow in front of the second shock. The first one is the one that gives you the rho 1. I mean, that's just one situation. There can be other situations where the initial states are not the same as for a single shock. And you derive the equations very similarly, even in that case. But it's just easiest to think in terms of shocks, at least in my mind. Okay. These are equations you really should memorize for shock physics. And if it's a single shock, you just easily stick the values for, this is the more useful equation, or all of them are useful, but this is the one you use most of the time. But if there's no particle motion in front, you get the single shock equation by letting U1 equal 0, and rho 1 would be rho 0 if there's no change in density in front. So for a single shock, this equation covers that, but it also covers the fact that you might have conditions other than P equals 0 and U equals 0 and rho naught in front of it. And that's why this one really is very powerful. Definitely should have that memorized. Okay. Had some other problems, such as 3-3. And this one is an example of symmetric impact, which we used actually in another experiment. But it's important to really understand this, and so I gave this problem which I think if you listened to the lecture and read the book, it's an easy problem. But I wanted to reinforce the thing because it's one of the best experiments you can do in shockwave physics, because you know some of the answers just due to symmetry. And that way, when you analyze your data, you immediately know if everything is right in your experiment. Now, you can't always do symmetric impact, but I'm just saying that if you have a choice and you're wanting to get absolutely good and extremely accurate data, this is having a flyer plate hit another flat plate without tilt, of course. This is one-dimensional compression. And the plates being the same material is called symmetric impact. And so what we want, the first problem is to demonstrate that the particle velocity is 1/2 the projectile velocity in a PU diagram. And I say that the hint is draw an XT diagram just at the point of impact, showing the shocks in both the projectile and the sample. Then after that, draw the PU curve, and you should notice from symmetry that this is true. So what I'm saying is that, okay, here we This is a problem we looked at before. Here we have a flyer plate coming in. It impacts at this point, and let's just say this is the sample. Has a shock going forward, has a shock going backwards. This is T and this is X, of course. And if these are the same materials, then we have some symmetry. So to look at the PU diagram, we have A, B, and C here. Well, this slope here, 1 over the slope is the flyer velocity, and it impacts at this point, sending a shock wave forward. So if we look at the material on the right side, that's principal Hugonio, because the shock is going from left to right, so the PU diagram for a forward-facing shock. Remember, I did go over that language once, and it is important because it saves on hard XT and PU diagrams. Forward-facing, and that means from the left to right on the screen. But now we have a shock over here in the flyer. Over here, that's a backward-facing shock, and it's also moving at this velocity. So that means we have to have a PU curve that's backward facing, but it also at the zero pressure, at just the point of impact, it has to be at the flyer velocity. If I've drawn this correctly, so this would be the PU diagram for the flyer, or a backward facing wave in the flyer. Okay. Well, these two curves, this curve and this curve are mirror images, actually reflected around this point, but we knew that this had to end up here. So we can slide this PU curve, this reflected image. It could have been, you can start over here and reflect it, and then just scoot it over to the point, and that, so this curve moves over to this curve. If you're doing it graphically, that's what you'd do if you had two pieces of graph paper. So basically, this is a mirror image, and if it's a mirror image, that means that this particle velocity here, from here, let's draw it here, from here to here, this UP is exactly equal to this UP. Let me take that out so and this is the particle velocity in the state B, and so which is behind both this forward-facing shock and this backward-facing shock. So this is the particle velocity in this plate 1 here. And you can quickly see then is that if this point here is U flyer, then 2 UP has to equal U flyer for symmetric impact because of the symmetry of these two curves. So This is very useful, since if you can very accurately measure your flyer plates on a gas gun, or in an experiment where you're throwing plates, even better than you can a particle motion. So this can be a very accurate number, and that tells you what the particle velocity behind the shock wave is very accurately, more accurate than other techniques. So that's what I meant when I said before that you actually know some of the answers because of the symmetry. And so, and this was really not a trick question. I hope it didn't fool you. All I really did want you to know is, well, then if this is the flyer velocity, then the particle velocity is just half of it. So it may have looked so simple. I hope you didn't think it was a trick problem, because it wasn't. Again, I'm trying to make sure that you remember this particular point, because it's a unique experiment, and not all experiments have symmetric impacts, but if you're going to work in the field, there's a reason people do it when they can, and it's very simply this symmetry. Okay. The next problem is another realistic problem with PU curves, and what I wanted you to do is I have a copper flyer impacting a tungsten plate. So this is still a flyer experiment. So there's a copper flyer. Whoops, it's supposed to have been yellow. Yeah. Hitting a tungsten plate. So this is not the symmetric impact, but you draw a similar curve on the XT diagram for this. And I give you the value of the copper of a flyer plate, what it's traveling at. And you can solve this graphically. You can use Excel, or if you have the equations for this kind of a problem all set up, then you can do that. So what I do is I use Excel, and I know I look up what the copper and tungsten linear USUP curves are in appendix, I think it's B, or I'm pretty sure it's appendix B. And I just then use my Excel program, and I get my, the tungsten is sitting there. Let's go back and remind you one other thing. Remember, for the XT diagram, you have a flyer coming in, and that's of copper. These should be parallel because there's no pressure in the plate. So this would be a copper plate, and we're drawing this right at the point of impact, and this would be a tungsten plate. And it's going to send a shock wave in, and of course a shock wave back into the copper. So that's, and I don't really need to go any further than that for this problem, because it's that simple, and that we can. So now what I've done is the shock in tungsten, that's the material on the right, so it has to have a forward-facing shock along its PU curve. Like I say, I got that out of the table and just put it in my Excel. And I knew that I had a copper plate coming at 0.1 centimeter a microsecond, but it's going, the shock in it is going right to left. So this had to be reflected. And in the textbook, it gives you an equation for reflecting these simple Hugonios that you could use. But, well, in fact, that's what I did for this curve. So I calculate what the reflected Hugonio is. If you didn't know that equation, you could have actually, well, let me finish this, and then I'll show you that you could have done it in a slightly different way. And both are correct. So where these two curves intersect is the only place where the pressure, in here and in here have to be the same. There is a slight interface here, which I didn't draw, but to remind you of. This interface does move off at a little velocity. But the plate's pressure when they're in contact like this after impact, there has to be equal. That's a boundary condition. And so if they're equal, that's the only place is where they cross. And so therefore that's the answer of the pressure and the particle velocity in both the copper and the tungsten. Now, if you didn't know the equation to reflect the copper curve, you could have taken the principal Hugonio for copper, and I'll just draw it because I can't do it accurately without numbers. But clearly, it's less impedance of. So, you could have gotten the copper Hugonio from the table, the PU curve, the principal one, and drawn it, and then you could have found where this reflection wound up at the right velocity. It would take, on graph paper, it's real simple. You take two pieces of graph paper with the two graphs, you turn one over and you just slip it along the axis here until you get to this point. But the point here is that you would have this reflected shock the boundary condition has to be here, the reflected shock of the copper. So that will be the purple curve, and you can keep reflecting that curve around this point on the forward-facing curve until the symmetry gives you this. But it really is simpler to look up that equation on how to reflect a curve that is just a second-order curve, and it's given in. I'm pretty sure it's chapter 2, I think. It might be in chapter 3. I forgot what page it's on. But so this is, again, simple impedance matching. And so this was the question for the A part. Then it asked, for the first shock in tungsten, what's the compression? Well, again, you go to like I said, Appendix B, and you get the linear USUP expression for tungsten, and that with the density. And if you just want to know what the shock wave is that you've discovered on the, you discovered that this is the particle velocity in tungsten behind the shock. So you just substitute it in, this equation. Because you have UP, that's what is on the graph. So it's really just simply solving a linear equation, and that answer is 0.4459 centimeters a microsecond. And then for the compression, it's you've just drove. That was one of the homework problems. You had V2 over V1 is equal to U2 minus U2 over U2 minus U1. Well, that isn't what I asked. I asked for V over V naught. But remember, from the V1 over V naught of a first shock is equal to U1 minus little u1 over U1. So you have both of these. And if you multiply this by this, you get, if you multiply those two, you get V2 over V naught. So you just can substitute in and do that. Let's see. And I forgot to do the second part. Now I'm so familiar with these problems. I'm finding that I go through them maybe too fast. What I said was correct, but obviously I just did the V2 over V1. And I didn't finish the problem because this is what Actually, I made an error here too. I didn't use this equation. Hopefully you did it right. I'm going to have to redo this. I'm surprised that I went so fast and not watched my equations. But what I told you is correct, and down here is V2 over V1 is equal to U2 minus U1, this U2 minus U1, and V1 over V0 is equal to U1 minus U1 over U1. And the multiplication of these two, you can solve or just say you can solve then for V2, V over V0. This would be V2 up here actually. So I'll have to correct my solution sheet on that. I guess the lesson there is that you should go through it slowly, and I'm so familiar with these equations, sometimes I just really buzz right through the problem and I'm not as careful as I should be. Okay. The energy equation looks like, except for maybe making an error in this equation, it's going to also be slightly off because of that error. But the process is, the V2 is equal to V0 times the correct compression. So this would be true, but again, this answer is going to be slightly off, but at least the procedure is correct. You need V0 also, and you need V to solve the energy. V0, of course, is the initial density, 1 over the density, and V is the solution of up here. So once you substitute that in, then you would have the correct energy. And then you go ahead and use the conversion factors of, once you get it into megabar centimeter cube per gram, you can convert it to joules, because remember 10 to the 5th joules is equal to 1 megabar centimeter cubed. Weird units, but it then would be come out in some value of joules, and then 41844, I believe it is, calories per joule, so then you can convert. So again, the process is here, but I made a slight error here, which I will correct for the grader, and we will correct your homework. Hopefully you did not make the same error I did. Okay. Well, that goes through the homework, and the reason I do that, well, apparently maybe there's two reasons. One is that I want you to have a experience of how the problems are solved and have a notebook with the correct solutions. So it's a case that we will correct that last slight error and give you the right answers, and so that you will have. But it's also a case that it's very useful to have this at a later time when you're not right involved in it, and you can look back on your notes and see just how a problem is done. Okay. Well, and the other point is that I think trying the homework is very important, even if it's sometimes a simple homework problem. If you think you really understand what the lectures are saying or what the book says, I found that until you try to apply it, you don't think of some of the issues of, is it consistent units, and how do you get this parameter that you have enough information to get, but you're going to have to solve other equations to get. So all that takes a little experience before you get really efficient. And so that's important for you to go ahead and do the homework and get that experience. So the last class, I showed you how to publish principal hugonios, how you can get lab speeds from them if there's motion in front. This particle motion. So this technique was based on the symmetry of forward-facing, backward-facing PU curves, and that's really getting into impedance matching, which is what we really want to get into today. And so we want to calculate the lab shock velocity of a reflected shock in PMMA when a PMMA plate is against a copper and a shock of 0.019 megabars in the PMMA plate. So we generate, so first of all, we're going to have we calculate we have a shock in PMMA, and it's against a copper plate, which is higher impedance, and you induce a shock of 0.019 megabar in the PMMA plate. Okay, so this would be PMMA. This is T, and this is X. And this would be copper, right? Yeah. Copper. So we put a 0.019 megabar shock in the PMMA, reaches this interface. It will reflect a curve and transmit a shock. Now, remember the rule of impedance matching is if it has a higher impedance at the boundary, going across the boundary, it'll transmit the same type of wave and it'll reflect the same type of wave. So that means that there's going to be a shock reflected back in the PMMA at this boundary. And to be actually correct, the boundary moves, and you need to always remember that. The boundary over here also moves at the particle velocity of 0.019 megabar in the plexiglass. So what we want then is the PU diagram for this. This would be plexiglass, PMMA. That goes in the first curve, and then we have a copper plate, which this would be copper. And if this is 0.19 megabar, it's actually 0.19, 19 kilobars. So it's not very high. You have to then reflect this Hugonio, the PMMA Hugonio, now I'm going to redo that because again, I tend to go a little fast on these problems since I've done so many of them, and that leads to some errors. Okay, so we give it. You can't do a impedance problem without having a boundary condition in the problem given. So this boundary condition was that we had a shock in PMMA, this one here, of 0.019 megabar. So that would be 0.019. So that means the PMMA curve, that's what I was trying to do and I hit the wrong color. This curve has to be reflected around this point. So if we do that, something like that, this would be the reflected PMMA curve. And as we've noted before, the solutions for the pressure between the two fields, this field and this field, because there's a boundary they're still in contact, they have to be the same pressure. Well, that means that the pressure has to be there. Now from this, if you have these answers, these are real answers, you have the pressure in the plexiglass, on the backward facing wave, remember you have this equation. And you know, if we're applying it to this problem here, and we went from this state, on this point, we can use this equation to actually, since we know U1 and this is U2, so we know this value, we know the density based on, it's the density of this point. So we know that. And we know P2 and we know P1. This would be, P1 and this is P2. So the only thing we don't know in this equation is the Eulerian, or the U2 minus little u1. U2 is the shock velocity going back, is this shock velocity in Eulerian or lab coordinates. And you have to account for the fact that it's going back into a flow of a particle velocity of u1. So what you then have then is u2, whoops, again you just solve this, u2 is equal to rho 1, actually P2 minus P1 over rho 1 times u2, little u2 minus little u1 plus little u1. So this is your Eulerian velocity that is going back. It's this one up here on the xt diagram, right here. That slope has to be 1 over this u2 because we're in lab coordinates. So if you do the impedance matching, you have, like I said, you just need the pressure, P2, you were given this P1, but you also get the particle velocity and this particle velocity, and you know the density state from the single shock wave for this. You have to calculate it. The V1 over V naught is equal to this shock here, U1 minus U1 over little capital U1. So you can get the rho 1 because V1 is equal to 1 over rho 1. So that gives you then enough information that you can actually determine the laboratory velocity of the shock that's going backwards from right to left from this boundary right here. And it turns out it's this equation. So now this is how you use this equation to determine the lab, the laboratory velocity. What did I do here? Okay. That's where I was at. Intuition wouldn't tell you, at least in my opinion, until you've really worked a lot of these problems, what that velocity would be. So you really need to use these equations to really determine the magnitude of the Eulerian velocity when it has motion in front. Now, if it's a simple problem, like if it's going to the right, that seems to always be easy, because if it's got particle motion in front of it, then the Eulerian velocity is just is going to be the disturbance velocity plus that particle velocity, so that when you subtract that particle velocity, you actually get the disturbance velocity. Remember, oh, I see what happened. It actually erased the equation I had. Remember on P2 minus P1 is equal to rho 1 U2, capital U2, minus little u1, little particle velocity minus that equation. I've mentioned at least once, maybe more than that, that really in this equation, this is the disturbance speed. Too fast on the buttons. This U2 minus U1 is really the disturbance speed in the media, and it goes into this equation, but that makes then the Eulerian velocity that you need to determine U2. So you have to actually be able to determine that to get the right magnitude. Otherwise, you wouldn't be getting, the balancing here of these two. Well, in this case, up here. So this just ensures that you do it right if you use this equation. Okay, I did that already. Okay, so that actually was another impedance problem. That's sort of the simplest impedance problem you have in shock physics. With the biggest problem is determine the Eulerian shock speed. You don't get that directly from the principal Hugonio if it's going from an initial velocity of a different value. So that's the only precaution I guess I can tell you is that you have to understand difference between disturbance velocity and a Eulerian velocity. Now, another thing we'll get to when we get to equations of state, the disturbance velocity is what's determined from an equation of state. It's said another way is that when you take an equation of state, it assumes there's no particle motion in front. And you just, like if you want the sound velocity, it's c squared is equal to dp d rho at constant entropy is by definition. And so when you get that value, that's a disturbance velocity. That's not a Eulerian velocity. Now, if there's no motion in front of that wave, then the two are the same. But if there is a particle velocity in front, you have to add or subtract to it to make it a Eulerian velocity in that coordinate system. And we'll go over that again in a little bit, but I just thought since equations of state really will become very important to us in the future, then you will need to realize that you're getting a disturbance velocity if the material is in motion that you're actually interested in. So so we've gone over the tools of impedance matching. This is again a very simple problem, and now we need to do some more impedance problems. And so what I'll do is repeat a little bit of what we did, but in going over this section 310 where I have a little formula for, or not a formula, but a few little drawings on the shock waves that you have in the impedance problems that you have. So a lot of the impedance problems will all start out the same. You start with an XT diagram, connected with a PU diagram, and you go as far as you need to. A lot of them can get complicated, so you may have to actually use more than one diagram, but we'll show you that in a little bit here. But they all start out the same, so you need to be given some conditions. You can't just draw the problem without that, of course. And so what we have then is, here's the problem we're wanting to make sure you understand, is a right traveling shock is incident on a higher impedance material, and the impedance, remember, is the density front of the shock times the shock speed, or velocity. Well, in this case it is shock speed. And so the second material has a greater impedance. That's what we're saying here. So that means that its density times its shock velocity is greater than the one on the left. So it has a higher impedance. And so what we want to do then is go ahead and draw the XT diagram. And first of all, let's just draw two plates, and this would be material 2, the higher impedance material. This is material 1. I'm going to just put it up here so it's out of the way. I think I'll draw this up here, and I'll draw a dash line, because that was the initial boundary condition, or boundary. But when a shock wave reaches the boundary, remember, it moves actually at a very small rate, which is actually 1 over the particle velocity behind the shock. So we have a forward-facing shock in the material, the low impedance material on the left. This was the same as the PMMA problem actually, but this is more generic, so that we can just get used to doing these diagrams. And another shock, and I'm going to just say that we don't, the boundary for the other material is way to the right, so we don't need to draw it because we're not interested. Normally we need to put the fields in to allow this to happen. So we would have a field A, which means, remember, this means that all the area here, the pressure is the same and the particle motion, all that, the field that is an area where everything is the same, the pressure, the particle velocity. And so we have field A, and we have field B, we have field C, and field D. Now, since I haven't talked too much about fields, let me just quickly make sure you understand that all this is, let me get rid of this initial boundary just to help us here. This is field C until another boundary occurs. This would be, field D, that whole area here. Again, the pressures and particle velocities are all the same until a wave or boundaries exist. And in this case, these fields are zero pressure, zero particle velocity for this problem. But they are fields, so everything in this field is, there's no motion anywhere in this diagram. So it's going to be important then to map these fields by their letters, A, B, C, and D, on the PU diagram. That's actually something that that's very important when you have a more complicated problem than this one. But it's best to start on these simple problems. So I'm going to go ahead then and show you the PU diagram. and put the labels on it. And if I go slow enough, I won't make an error. Well, the low impedance material is here, and that's the principal Eugonio for 1. Oh, I forgot. Actually, when this hits here, remember I thought something was wrong with that. Again, let me go back to correct that. This is the initial boundary. So I'm actually got ahead of myself again because I forgot to reflect that shock. Remember, we have a shock going in, hits a higher impedance material that reflects a shock and transmits a shock. That's the little rule of thumb that I said you needed to remember. So the fields, A, B, C, there would be D, and then another one, and E. So this E field, it's a smaller field than I had drawn before. And then the D field up here until another wave or something occurs. So there was one extra field, and when I started my PU diagram, I noticed that. And actually, that happens a lot when you're doing these things. You might have to start over thinking, realizing you'd left something out. Well, so let's go back and go over the problem. We have on this first shock in this lower impedance material, and it's going to be along the PU curve, principal PU curve from the right to the to left to right, I mean, forward-facing shock. And it sends a forward-facing shock into the higher impedance material, and so that has to be material 2. And we also know that at the boundary, we'll have a condition, I'm going to go back to the black. This is going to be the E fields. The E field is the one that has to be given for you to solve the problem, or at least one of these fields you have to have more information, and usually you're given what is the pressure of the say this first field, the E field. Well, if you know that, then you know that you reflect this Eugonio around that point, and where they cross is the C field. Or what we have is, let's start with A and B. We know those are 0, and we go from A to E, which is along this Eugonio. That's over here. That's this shock right here. And now, but in PU space, it's this one. It winds up at field E. So we see then that field E is represented by this one point. This point right here. Now, if you can move around to whatever part of the XT diagram that you feel you can make the easy solution, but you notice that from this field B across this forward-facing shock in the higher impedance material, C, you get to state C. Well, it has to be along this curve somewhere, and at this point, we have to decide that well, we know it's where it crosses, but you need to continue to work on it because this is going to be the C field here. But if you went from A to going back over to the XT diagram, and let me see if I can show you this. I went from A, and I'm going to E. So A to E is on this curve. Now I'm going to jump from the field E to field D. Well, that's across a backward-facing shock, so it has to be along this curve. Remember, it's the same reason we say that the answer has to be where it intersects. But that means both C and D fields are represented because they have a boundary here, but the two plates are together, therefore the pressure across them have to be the same, and so does the particle velocity. So then that's the excuse me, the solution. And the difference is that I've labeled what the solutions are. And again, this will become very handy when you do other problems. Well, this is the XT diagram, a little better than I did. And so I gave you that example. I'm going to take a break at this point, and we'll come back and let you do some problems. Okay, let's take a break. Excuse me. Okay. All right, we're back. So now I'm actually going to have you go over this same problem, but I want you to do it on your own. Here's the case one, a right traveling shock incident on a higher impedance material. So I'm giving you the XT diagram with the fields. And so what I really would like you to do is the PU diagram. Take about 5 minutes to do this and label the PU diagram. So make sure all the fields in XT diagram are located on the PU curves. And I'll do this again after you do yours. So I'll give you about 5 minutes before doing another problem. So take your time and see if you can do this. About 1 more minute. Okay, that should be enough time. So here's your XT diagram. Just review it quickly. You have a higher impedance material on the right over here, lower impedance material over here on the left. You have a forward-facing shock, and the lower impedance material intersects the boundary between the two. A shock is transmitted, because remember the rule is same type of shock will go be transmitted if in either case of the impedance on the right. But what is different is what is reflected. So if it's a high impedance on the right, it reflects a high shock wave. Reason is really it's got to bring up the pressure in that first plate, because the higher impedance will be a higher pressure. So they have to be equal, of course, across D and E. So you get a forward-facing shock in the higher impedance material, a backward-facing shock in the lower one. They have a boundary between them that moves at the particle speed of this shock. So this boundary is 1 over the particle speed of the shock, this shock here. Turns out it has to be the same for the backward-facing shock, because this field has to be, D and C have to be in equilibrium. Boundary condition for the plates to be together. Okay, so that being the case, this is the answer in the PU diagram, and this is a completed impedance matching problem of the first, very simple one, just one reflection. But you can see that with the paths here, you can even sort of write how you're going to solve it. You go from A to C, which is a shock in the lower impedance material. Then you go from B to C, forward-facing shock in the, I'm following these paths here, along the higher impedance material. And then C to D has to be along this line, a reflected line around, actually it's around E, it's reflected. But where it crosses is C and D, which gives you the boundary being equal, which means back to, C and D have to be equal in the XT diagram. And of course they are, because that's where these two curves intersect right here. So that makes them equal. It conserves the momentum and energy and mass. It's a graphical way of doing it, but that's what. And like I said before, you have to have some information to start the problem. Typically, it's something about the first state E. It's usually, the shock here typically is given. But if it's not that one, one of the other states have to be given, or you can't do the problem. Okay, we're the next problem is case 2, where a shock is incident on a lower impedance. Otherwise, we switch the plates. And so it is slightly different. And let me go over it quickly, and then I'll have you do it again, so because I want you to map the fields. But here, you have 2 plates. I'm just going to draw a boundary between them. The one on the right is lower impedance. So this is lower impedance. See if so this is 2 and this is 1 again, but this is a lower impedance material over here. So what you get then is a shock. Actually, I probably should draw the shock, and this is the boundary, and then it goes off. So you get a shock transmitted. Again, the same rule. If you have a shock coming into a boundary, it'll cross the boundary as a shock. But if it's a low impedance material on the right, it reflects the opposite type of wave back into 1. That's the little rule that you're supposed to have memorized. So instead of just one wave, remember now it's a relief wave, because if it's a shock wave going in, it's got to be a relief wave going back. Remember that we treat relief waves as a fan of 3 lines, so they're relief shock waves, really, step waves, I guess. It's an approximation, but for doing this by hand, what you have to do, it gets way too complicated. As I said in the book and the other notes, is that once you start getting to need for really more accurate equations, you have to use a code. When the thing gets more complicated, then it's worth it. But you really learn more physics about and intuition about the problem by doing this, even though you are making a simple approximation. So you'd get 3 relief waves. The reason you get 3 is, remember, a relief wave is not a steady wave like a shock. So it represents, if you remember the diagram, here's the shock, and now it has a relief, but we can approximate it as 3 little relief waves. You could do more, but I mean, I just choose 3. Now they're step downs in pressure, so they're actually going from here, and it drops to here, and then from here to here. Well, they have different velocities. If you even this case, this will have a velocity. I'll just say one velocity and this would be velocity 2, and this would be velocity 3. Well, V1 is greater than V2, which is greater than V3. So that's why you have the fan. And again, remember the slope of the curves in the XT diagram is 1 over the velocity. So the highest velocity, this V1, is going to be this one. So it'll be 1 over V1. This will be 1 over V2. And this would be 1 over V3, which is the slowest, which gives you the highest slope in the XT diagram. So here you also need to go ahead and label all the fields, even the fields between these fans here. and you need to then find what they are on the PU diagram. So let me show you, this is the problem, and I want you to go ahead and see if you can do the PU diagram for this problem and label the fields just like we did before. And so here, I'll leave this up on the screen. And so again, this is a shock going into a material, two plates together. The shock is in a higher impedance material to begin with over here, and the material on the right is lower impedance, and therefore it sends back this rarefaction fan, and you need to do the PU diagram, and you do everything as if these were little shocks, so you go from D to E to F to G. Well, go ahead and see what you can do, and then we'll show you the answer. And these are the two basic ones that you will do, and you'll do this type of thing throughout even more complicated PU diagrams for impedance matching. They'll have some similarities of one of these two types. So that's why we wanted to really go over these two to begin with. So probably don't need the 5 minutes, but I'll give you about 3 or 4 minutes to go ahead and now do the PU diagram and label the fields that are given here in the XT diagram. Okay, that should be enough time. So let's go ahead and review what it should look like. This would be the answer. Essentially, let's go back. The G field is given. That's, again, we said that you always have to start with some field. And so, again, you had a forward-facing shock in a high impedance material. So it has to be along this eugonio. And it sends a shock into the lower impedance. I'm sorry, that's the wrong eugonio. It's a higher impedance shock. Has to be along that. So the first plate is higher impedance, so it has to be along that curve. And when it hits the boundary, it sends a forward-facing shock into the lower impedance material. So the answer has to be along that curve. Now, the easiest thing to notice is that you go from the G field, which is the given information, and it steps down across the relief waves from F to E to C. And when it finally gets to the final state where C and D are common, they have to be equal. And so that's so what you notice that I've done is divide the by dividing these into 3 steps. Essentially, I've taken they're a third of the pressure from G to C is in each of these points. So it divided them equally in the pressure, and so they just show that you go across those fans, and that the last fan where it bounds on C and D are the same, because again it's a boundary and it's staying together, therefore pressure and particle velocity have to be the same. And that's what that means. So that's the answer to the second case, where you have 2 plates together, the first one higher impedance and the second one lower impedance. Later on we'll see that when we do these problems that actually the plate on the right will separate from the one on the initial plate with enough time goes and enough waves go to the free surface and come back. That's important for if that material on the right happened to be a gauge or something and it doesn't stay in contact with the sample you're looking at, you can have problems. We will go over that in some detail because gauges are essentially thin plates, and I'll go over some of those examples. But now you've done 2 of these cases, which are sort of the more important 2. And if you didn't get them right, you really should maybe take tomorrow and sit down and draw both the XT and PU diagram just from the fact that you're having a shock coming into these 2 plates, and you have the in one case the higher impedance on the right, and the second condition is a lower impedance on the right. And go ahead and get to the point where you really can reproduce this answer and understand why it's happening. And because that's the basis of impedance matching, and even the harder problems, you have to be able to do these simple tasks, and they can be part of another problem. And they really allow you to keep the bookkeeping of where the states are in the fields, and if without that you'd get lost with just drawing the XT diagram. You wouldn't really know after a while just whether it's a shock or a relief wave in more complicated problems. So okay, here's just a case where I'm showing you again that you have PMMA on the right, and you have principal copper curve. And so in this case, the copper curve is on the left. So you have copper and you have PMMA. And this just puts real numbers to it. So if the initial condition would be given, and that would be like it'd be 200 kilobars or 0.2 megabars. So you'd know that's where you reflect your copper curve, and it comes down. Where it hits the PMMA curve, that's the shock that goes into the PMMA along the principal curve. And notice that it's only 39 kilobars, so it drops from being 0.2 of a megabar all the way to 0.039 megabar in the plexiglass to allow this to be across that boundary to be the same. So the plates staying together requires that pressure to drop in this situation. But again, we've done separately drawn PU curves for real materials. Now we've done a couple of little examples of material that's a low impedance material on the right, like that was one of our problems we just did. This just puts values on the PU diagram. But again, experience tells me that when you start a problem, before you do the real numeric problem, like I was just showing you, do your XT diagram and PU diagram in this graphic form without numbers. Because now you have intuition of what the problem is all about and what should be a wave and what should be a relief wave in the fields. Then once you do that, so that's your first step, and I sometimes call this, we'll draw the impedance matching cartoons. They're not cartoons, but I mean just the unlabeled PU XT diagram. And then do your numeric one, so that all you're doing now is that you know what how this PU diagram should be. You just don't have the numbers until you put it in something like, well, this is an Excel plot again, and gives you the real answer. So this would actually be a design, if you did an experiment where you had a shock in copper of about 200 kilobars and a plexiglass plate next to it, you actually would measure, if you had a gauge or a camera, to measure the properties, either the particle velocity or the pressure. That's what you'd get within experimental air. So that is an impedance matching problem that gives you a way of designing experiments when you're doing experiments with particularly a gas gun, but also a flyer plate from a different source, such as an explosive flyer plate that the explosive drives across the gap. So you can actually anticipate what the answer should be, and if it isn't, then there's something that you have to investigate. And again, this is graphical conservation of momentum and mass and energy, and it's really more graphing than we usually see, but this field actually uses this a lot. And so when if you're reading the literature in the shockwave field, you'll see curves like this. Okay, now sometimes we have what's called a free surface. So if we have a XT diagram and we have a shock coming into this material and there's a free surface here, means a vacuum over here. A lot of times even air would be equivalent. Well, this free surface with this shock in this material, this is a shock going left to right. And now you have a vacuum. Well, this surface has to move. So it moves off to the right. And there's a relief wave fan that goes back. Because remember, a vacuum is a lower impedance material than anything. So it will be a fan. The reason it has to be is that the pressure at this point, just outside in the vacuum, has to remain zero. As long as you're staying away from being inside the surface. That's the boundary condition because the vacuum cannot sustain a pressure. Well, the only way that can happen is for the pressure in the solid sample or condensed matter sample to go to zero pressure here. This last field over here has to be zero pressure because outside in the vacuum it has to be zero pressure. So these two fields have to equal because that's the boundary between them. Just like we drew a boundary between real condensed matter. One of the advantages of this, though, is knowing this, is to do the PU diagram and the impedance matching. But you'll recognize that if you can ignore strength, otherwise no elastic waves, just this is a fluid, is it the velocity of this free surface it's the slope of that line, but the velocity of this free surface for a fluid is equal to is equal to twice the particle velocity behind this shock here in this field. It's also due to a symmetry argument. And this is very useful in experiments where you want to know what the particle velocity is inside the plate behind the shock. But you can only measure the free surface velocity. It turns out in a fluid this is exact. If it's solid, it's not. And so at high pressures for a solid, this is still a good approximation. But if you're down near the elastic limit of a solid, it's not a good approximation. But we'll get to that when we do solids in the second semester. So this is often used approximation and to get equation of state data because you can easily measure this free surface with a camera or pens, and we'll talk about that when we talk about experimental techniques. So, how do you do the PU diagram? Here again is your free surface and your fan. And so what we can do is we notice that, again, F field is given, and it's in a solid condensed matter material. So it's a principal Hugonio this way up to the field F. And then we want to go from F field to the E field to the D field to the C field. And we know, just from what I told you, is that we know this is P equals 0. This has to be P equals 0. So we know that it's going to be lower pressure. And besides, going from F to E has to be across a relief wave. And it's in the same material. So this is material 1, this is material 1. So but the relief waves over here are backward facing right to left. Well, that means they have to be on a reflected PU curve. In fact, it has to be this one right here. So in going from F across, this is an E, not a C. I was looking for it, and I was saying, what's going on here? I didn't make that error. It's just somehow it didn't come out very good. That is an E. So from F to E, and again, I split it, notice it's 3 fans, so it drops in 3 increments of pressures. Again, this is like a third of the pressure drop. This is a third. It isn't perfect because, again, I'm not putting numbers on it, but that's roughly what I'm doing. So obviously it goes from F to E and then E to D. It has to stay on this reflected curve. Otherwise, it's not conserving momentum. And so clearly then it goes down to the P equals 0. Well, notice that this is the same curve we did before where it was symmetric impact. It's reflected now. It's the same curves, but it's slightly due to a different reason. It's because there is a free surface. And since this is reflected mirror image, you know, we actually went over this, is that means that the particle velocity from here, let me put the ballpoint on instead of that. Just due to symmetry, this particle velocity from here to here is the same as from here to here. This is the delta P, delta UP. So C has 2 UP, and UP is actually at F state. So this, you know, this is this state here is equal to UP, and P equals 0 right here. So essentially what we're doing is saying that 2 UP is equal to this UC. Well, UC is equal to the free surface velocity. And so there we go. From symmetry, we've derived this approximation for fluids. And again, like I say, you can treat solids like aluminum and copper and things that are, when they're at least 10 times the yield point, this approximation gets within better than 2%. You go higher, it could even get better. You go too high, actually, the truth is it doesn't get better when it goes really up into the megabars. And we'll talk about that again when we get to solids in the second semester. That's because materials can change their yield strength under compression. And there's been studies showing that, whereas before everyone used to assume that it would be constant, but it's not. So, okay. So, like I've mentioned before, is that free surface is really actually pretty easy to measure. A street camera with a tilted mirror on it, on the surface, and again, I'm going to go through those techniques. Or you can have just closure pins away from the surface, and once they're impacted and you know the distance and the time, that tells you the velocity. That's the old technique that was originally done at Los Alamos. And so most of the early work was done with measuring free surface velocities on metals, and that's because all their work was done with explosive drivers, so they were in the hundreds of kilobars. It's where this strength did not really come into there was no issue because the errors were so small for using this approximation of free surface velocity is twice the particle velocity behind the shock reaching that surface. So, okay. I'm just going to mention something new and then we'll be done for the day. Just so you're aware of it, we're not really going to treat this it's a special problem that has a few materials that you have to watch out for it. It's called a contact discontinuity, and it's really could be a problem for certain highly inelastic materials, but most of the times it's really not an issue, and it's just a case that I want to show you what the problem is. If you have, for example, two waves interacting, or actually colliding, two shock waves colliding, you have this shock is going to run into this other shock. We can use impedance matching to find out what is the final state. So these are just two snapshots. We're taking a snapshot like a picture, and then this is before the collision, and over here is after the collision. And you see that you have a shock, two-step shock. It wouldn't be that perfect. They would be smoothed out, but this gives you the idea. And the XT diagram for this is down here, whereas you have the first shock 1, and I'm putting the collision point is the x equals 0 axis, where these two shocks really collide. So you have the forward-facing shock here, it's going here, and you have a backward-facing shock coming in here, and they're going to collide at that point, at where 0, x equals 0 and t equals 0, because we can arbitrarily pick where our coordinate system is. And so what we want to do then is decide, well, what's going to be the state in this material. It's the same material. There's no two materials. This is all in one material. These somehow you generated shocks from different sources. Well, when this first shock comes in from the left to right, the standard one, it interacts, and so it changes its velocity and particle velocity. So there's a change. And the same thing happens to the one going from right to left. It changes to a new state, or a different velocity. So after they collide, they pass each other, so two shocks still go. One goes to the this probably would help to have the arrows on this, so that shock, they went through each other essentially, and now they leave a state here this equal because they've passed through each other. But there's still waves. This wave S4 is going from right to left, and the wave S3 is going from left to right. So if on a PU diagram, you start with the down here the state A. This is where zero pressure is. That before anything's happened, they haven't collided. And if you go from across this shock from A here to B, it's a backward-facing shock, so it has to be on a backward-facing eugonio. And if you went from A to E, if you're going now, let's use a different color, I think. Now we're in state A, and we're going to cross this shock that's a forward-facing shock, so it goes from A to E. Well, remember, this is A, and so it has to be on a forward-facing PU curve, and this one had to be on a backward-facing PU curve. So once we get to state B, and we notice that from state B we have to cross the from B to C is across a forward-facing shock in the same material. Again, remember, this is all the same material. So you have to go from B to C in a forward-facing shock, so you have to reflect the PU curve at this point and get a PU curve from here up to this direction. And the same thing back here from E to D is across the backward-facing shock, so it has to be reflected. This PU curve here has to be reflected at this point, and where they cross is where the answer is, of course, and that's where D and E, or D and C, come out. Well, that's this state, D and C. It's, the equal pressure here. So that's the solution of two waves colliding. But what can happen is that although the pressure and particle velocity are the same, because of the different magnitudes on the shocks on these, the temperature where along these boundary here, notice this boundary here, the temperature on the left and right, on here in this field, well, just say in the fields, in D and C, even though the pressure in D and C are the same, showing in the PU diagram, the temperatures don't have to be, because the shock difference, it's not linear. Temperature's not linear with shock pressure. And therefore, you can wind up with, if we look back again at the XT diagram, this area here can have one temperature, but it's at the same pressure as the other field, and this will have a different temperature. So when that happens, it's called a contact discontinuity, and if you are measuring a property that's sensitive to temperatures, then you may have an issue here, and you may find different answers than you expect. This is very rarely a case, but there are some cases, like I said, in highly inelastic materials where the properties are really temperature dependent, and therefore then you actually wind up getting some interesting results. So if you have really highly compressed material, this also can reach high temperatures, and because of like if you had porous solids, we know that porous solids really, most of the energy you put in that turns out to be thermal. But it's also depending on the shock jump, the delta. So you see the delta in pressure, the delta from this shock to this shock, this delta P is different than this delta P. So the material on the left here is going to be cooler than the material on the right because a shock of a different amplitude went through it, even though it did wind up leaving the states with the same pressure and particle velocity. Now, in principle, that's always true, but it's usually a degree or so, and it doesn't really matter. But for certain materials, if they're highly porous or highly compressible, I guess, that temperature difference can be more than just a degree or two, and therefore you may run into some different phenomena than you would expect with different, like say, highly inelastic materials, or if you had, well, for some reason, if this happened to be a chemical, a material that could go under chemistry, that could be a big thing, such as explosives, actually. That could actually, that temperature difference could initiate chemistry, even though the particle velocity and pressure were initially the same. Temperature is known to really drive chemistry, not pressure. So there would be a case where this could be important if you were doing experiments, initiation experiments, and you're only looking at the final pressures, thinking that you could use two waves like this to reach a certain pressure. Turns out that you're going to have different temperatures in different parts of that material, and it could drive chemistry at one side of the material faster than the other. So that would be maybe a good example of it. The properties of elastic materials would change. That means also the hugonias would change a little. They wouldn't be the mirror images actually as drawn. That's the problem there, is that you can't use the mirror images because their PU diagrams are affected by the temperature, and we have assumed that temperature is not going to affect the hugonios. And typically, like I say, only a couple of degrees would normally be in metals, and so that's not, you can't detect that. There's no, after all, we can't even measure temperature in shock waves inside condensed matter yet, unless they can, unless they're Raman sensitive. We can take the Raman spectra of those materials and get a temperature, but that's the only way that we can do temperatures at this point. I'll bring that up again at a later time. I'm going to just mention this. I don't think I'm going to go through this example today. Thin foils are used as gauges inside of shock materials and even sometimes on the surface. So it's important to understand how they mechanically reach a final pressure particle state. As soon as you have as you saw, that when you have two materials against each other, the equilibrium at the boundary occurs, but if you have another boundary like a free surface, then you have another relief wave coming back. Or if you even have three materials, like say two of them are the same material, high impedance one, then a low impedance foil that's thin, and a high impedance material, so that eventually you know that the shock wave is going to, in the thin foil in between, it's going to get to the same pressure that's in the shock in the other materials, but it rings up. It doesn't happen with one shock passing through it and it's there. It actually has waves ringing up. So there's a time dependence that affects gauges, and it eventually gets to the final pressure, but it takes a little while. And so you have to know this to interpret your records. And one gauge that I've used a lot is a Manganin gauge. It's a piezo resistance gauge. And so knowing the response time of a gauge is very important, because if it's too long, you actually won't get an accurate reading. So the rise time really needs to be designed to meet the requirements of the experiment. So what we're going to do is talk about these foils. We're going to do the XT diagrams for them and show you the different situations, and we'll come up with one particular scenario where you don't want to put a gauge of low impedance on a surface of another plate with the gauge having a free surface on the far right. Essentially, the gauge will separate and it stops recording what you want. It may record some signals, but they're not part of the shock being transferred from the plate on the left. So that's a bad design. Some people still do it. So I just thought it's important to go over that scenario so you really understand that you don't want a low impedance gauge on a high impedance surface because it'll separate and it won't record the data you think it will. It would be okay if it's in between two plates because it will ring up, but again, you have to then allow, typically the rule of thumb is 3.5 reverberations, and it gets to about 90% of the pressure it's going to reach. But that's sort of the time for the gauge. So if you want to do nanosecond gauges, you're going to have a problem. You just really can't do that. You have to go to optical techniques. So this really goes towards experimental techniques. And that's why I want to go over it before I get to the experimental techniques. And it is just impedance matching, and we'll go over some of these details on these graphs, and I will show you for an example that they can get more complicated than I've. See, I've been only having this this lecture has only had you worry about these fields down here. Notice all these fields. And that's because notice you see we're getting waves off of every boundary. You know, there's waves, and they're reflecting waves. You have to take those into account on a real problem. And clearly you can't continue this forever. So again, that's where you go to a code once it gets too complicated. But for a lot of problems, you can do this and get accurate answers. A lot of times you'll also see the trend, so you know what the final answer has to be. It may take more time than you want, but you'll see that also is that you can see the trend once you start these. So this is a lot more complicated than we did earlier in the lecture, but it's very important for experimentalists, and so we will go over some of these. Again, here's another one where I'm showing you. Well, it's the same. It's just more of this problem. That's where I have to actually use extra graphs to actually do this, and so this is what we will take up next time, and we'll start doing these impedance matching problems to lead into the chapter on experimental techniques. And hope you have a good time doing the homework, and I will definitely try to slow down when I do these problems, and so I don't make another simple error like I did today. Somewhat embarrassing when I look on the screen and I recognize that that's not right, and I just did that 2 days ago. So, okay, we'll see you the following week then, and we'll move on with more and more interesting things, hopefully. As I said before at the beginning of the class, what I really want to do is get you doing simple impedance matching problems by Lecture 4, Class 4, that's today. We've done that. Doesn't mean you really can do all the problems that are out there by any means, but you have the basic ideas now and the basis for really doing them. And so you really have learned maybe more than you really understand at this point. But that will come, and you'll see how useful that is, particularly if you're working in this field. That this is really the underpinning of understanding what's going on, and when you read papers and design experiments, this is the technique that everyone has to use. And once you get this down solid, then things, I wouldn't say they become simpler, but you can do harder problems by knowing how to do this. Okay, so we'll see you next week.